All right, welcome to our unit on nuclear chemistry. Today's topic is average atomic mass. Lesson 1 of 3, your objectives are as follows. You will learn what isotopic mass is in terms of atomic mass units, AMU. You will understand percent abundance and how it applies to isotopes for a particular element. You will learn what average atomic mass is and how to calculate it given isotopic mass and percent abundance. For your quick write, how could you find the average weight between 3 students who weigh 145 pounds, 123 pounds, and 114 pounds? In a class of 30, 18 students have brown hair. How could you calculate the percentage of students with brown hair? Okay, and a little review here. What is the mass number of an isotope? What is the atomic number of an isotope? Okay, go ahead and pause this while you do a quick write. I'm going to move on here. All right, so an atomic mass unit, AMU. If we could weigh or mass a proton or neutron, it would have a mass of about 1.66 times 10 to the negative 24th grams. Well, that's an incredibly small number to work with. A more convenient unit to measure the mass of a proton or neutron is the atomic mass unit, or abbreviated AMU. Okay, so if you remember, 1 AMU is equal to 1.66 times 10 to the negative 24th grams and is defined as 1/12 the mass of a carbon-12 atom. Okay, so let's take this incredibly small number here and make it equal to 1 AMU. So a proton has a mass of 1.007 AMU and a neutron has a slightly heavier mass of 1.008 AMU. But notice they're about the same, okay, but a neutron's slightly heavier. So isotopic mass. If you remember, atoms that have the same number of protons but different number of neutrons are called isotopes. Okay, this should be a review. They are the same element, but because they have a different amount of neutrons, they naturally have a different mass. So isotopic mass is the mass of a specific isotope. So consider the carbon-12 isotope here, for example. Okay. If we could weigh or mass a single carbon-12 atom, it would have a mass of about 12 AMU, 6 protons and 6 neutrons. Okay. If we add a neutron, so we just add a neutron here, notice we create the carbon-13 isotope with a mass of 13.004 AMU. And if we add yet another neutron here, okay, to carbon-13, we create the carbon-14 isotope with a mass of 14.003 AMU. So notice the isotopic mass changed with the addition of each neutron. Carbon in all elements occur in nature as a mixture of isotopes. Some of these isotopes are more abundant than others, while others, okay, like carbon-14, are very rare and less common in nature. So, for your notes, what is isotopic mass? Okay, question on the left-hand side, answer on the right-hand side. Go ahead and pause this while you write. I'm going to move on here. Okay, so natural percent abundance of isotopes. Natural abundance is the amount of isotopes in a percent for a particular element found in nature. Okay, so for example, let's say this pie graph over here accounts for all the carbon atoms found in nature, 100%. Okay, well, the carbon-12 isotope is the stable form of carbon and accounts for about 98.9% of all carbon atoms found in nature. Therefore, we say carbon-12 has a natural abundance of 98.9%. So in other words, if you were to pick up a sample of carbon, 98.9% of them would be the carbon-12 atoms or isotopes. Another isotope of carbon, carbon-13, is less common, making up about 1.01% of all the carbon atoms found in nature. And isotopes like carbon-14 are very rare and account for only about 0.014% of all carbon atoms found in nature. So therefore, we say carbon-13 has a natural abundance of about 1.01% and carbon-14 has a natural abundance of 0.014%. So let's take a look at one more element, magnesium here, and its natural abundance. So let's say once again this pie graph accounts for 100% of the magnesium atoms found in nature. Okay, well magnesium has 3 isotopes. Magnesium 24, which has a natural abundance of 78.99%, okay, and magnesium 25, which has a percent abundance of about 10%, and as you might have guessed here, magnesium 26 has a natural abundance of 11.01%. So notice they always add up to 100% here, okay? So what is the natural percent abundance? Question on the left-hand side, answer on the right-hand side. Please draw the example for your notes. Okay, go ahead and pause this while you work on this. I'm going to move on. All right, so practice here. Complete each table here below. And remember, the percent abundance must always add up to 100, okay? So determine the percent abundance of chlorine 37 and the percent abundance here of strontium 84. Go ahead and pause this while you work on this. When you're ready to check your work, hit play. All right, let's see how you did. Okay, so, well, remember, they have to add up to 100, so 77, okay, minus 100, well, that gives us a percent abundance of 33% here. Okay, so the chlorine 37 isotope has a natural abundance of 33%. Okay, well, add these all up and subtract them from 100, and that will give us the percent abundance of strontium 84, which is, okay, about 0.5%. All right, so hopefully you got these right. Okay. All right, so average atomic mass. All right. Average atomic mass, or weight, of an element is the weighted average of all the element's isotopes based on their natural abundance. The average atomic mass for every element can be found on the periodic table, directly below the atomic symbol. So, looking at your periodic table, you can see that hydrogen has an atomic mass of 1.007. Well, remember, that's the mass of a proton, about, okay? And most hydrogen atoms are made up of a single proton. So helium here has an atomic mass of 4.002. Notice they're not perfectly even numbers. Carbon, okay, has an average atomic mass of 12.001. And magnesium has an average atomic mass of 24.305. So like I said, notice the average atomic mass, it's not a perfectly even number. Well, why is that? So remember, the atomic mass is an average number based on the weight of isotopes and how abundant they are in nature. If all carbon atoms were carbon-12 atoms, then the atomic mass of carbon would be a perfectly even number of 12, 6 protons and 6 neutrons about. Okay, but as we just learned, 1% of carbon atoms in nature are carbon-13 atoms, and 0.014% of carbon atoms in nature are carbon-14 atoms. By averaging the percent abundance and weight for each isotope of carbon, we get an uneven number of 12.01. So, for your notes, what is the average atomic mass? Okay, question on the left-hand side, answer goes on the right-hand side. Go ahead and pause this while you write. I'm going to move on. Okay, so calculating average atomic mass. Here's where it gets a little tricky, so listen up. So, average atomic mass can be expressed by the equation here below. To calculate average atomic mass, okay, we multiply the exact mass of each isotope in AMU by its percent abundance and divide by 100. Okay, so for example, let's calculate the average atomic mass for carbon here. So the most abundant isotope of carbon, if you recall, is carbon-12 and carbon-13. Okay, so we're only going to look at those two isotopes. To calculate the average atomic mass for any element, we need two things: the mass of the isotope and its percent abundance. So carbon-12 here has an average atomic mass of 12 AMU. Okay, so 12 AMU, that is its isotopic mass. And if you recall, carbon-12 has a percent abundance of 98.9% in nature here. Okay, so there's its percent abundance. Now let's look at carbon-13. Carbon-13 has an atomic mass of 13.004. Okay, so that's its isotopic mass. Okay, well, unlike carbon-12 though, remember carbon-13 is much less abundant in nature, and it only has a 1.01% abundance. Okay, so that's there. Okay, so we have the isotopic mass. Okay, and we have the percent abundance for carbon-12 and carbon-13 here. So substituting these values into our equation, we get isotopic mass, okay, 12, okay, and its percent abundance is 98.9. Okay, now for carbon-13, okay, the isotopic mass is 13.004, and its percent abundance is 1.01. Okay, multiply all these values, okay, and add them up and then divide them by 100 here. Okay, so solving for the average atomic mass of carbon, we get 12.011, which is equivalent to the average atomic mass for carbon seen on the periodic table. Okay, so let's look at one more example here. Recall that magnesium has 3 isotopes, magnesium 24, 25, and 26. So the table below summarizes their mass percent and percent abundance for each isotope. Okay, so let's substitute these values into our equation. We get, okay, let's look at magnesium 24 here. Isotopic mass, 23.985. Its percent abundance in nature, okay, 78.99. All right, magnesium 25 now. 24.986 multiplied by 10%. Okay, then magnesium 26 isotope has a mass of 25.985, and the percent abundance, okay, for magnesium 26 is 11.01. Okay, so solving for the average atomic mass of magnesium, we get 24.305, which is equivalent to the average atomic mass of magnesium here, seen on our periodic table. Okay, so go ahead and practice here. All right, when you're ready to check your work, hit play. All right, let's see how you did. So the average atomic mass of copper is 63.546, which should be the same average atomic mass seen on your periodic table. Okay, let's look at lithium now. Hopefully you got an average atomic mass of lithium as 6.944, okay, which should be the same number lithium, okay, has on the periodic table. All right, so hopefully you got those right. Okay, so go ahead and summarize. Remember, you can always write your own. Okay, go ahead and pause this while you do your summary, and we'll see you next time.